So our last related rates problem we're going to do deals with a ladder sliding down a wall. So we have a 13-foot ladder leaning against a house, and its base starts to slide away. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. So we're dealing with this ladder leaning against the wall, and if you think about leaning your surfboard up against the wall, and maybe it starts to slide just a little bit, and starts to speed up, and by the time it's sliding to where it almost lands on the ground, it's going to slap on the ground, right? Because it's sped up. So that vertical rate of change the vertical value is changing. It's a rate of change. The angle measure is changing. How fast the base of that surfboard or ladder is sliding out against the wall is changing. So we're going to look at this problem. We have some values that don't change. 13 is never going to change. The ladder isn't going to suddenly grow in the middle of the problem. This is a 13-foot ladder. But we do have a moment situation. So this 12 feet from the house, and the rate at which the base is moving at 5 feet per second, that is at a specific moment. Those are things that change throughout the problem. So those are numbers we want to not use until we get to the very end. So if we want to determine for part A how fast the ladder is sliding down the wall, we need an equation to relate what we're looking at. So I'll call my horizontal distance x and my vertical distance y, and I can create an equation because I know the Pythagorean theorem, x squared plus y squared equals 13 squared, which is 169. So this relates my horizontal and vertical measurements with regard to the measurement of the hypotenuse, which isn't going to change in this case. So if we want to find how fast the ladder is sliding down the wall, that means we need to find dy dt. So that means we're going to take our function and differentiate with respect to t. So I've got x squared plus y squared equals 169. Differentiating with respect to t, I get 2x dx dt plus 2y dy dt, and then the derivative of 169 is 0. So if we want to know the rate at that moment, well, we know at the moment that the base is 12 feet from the house. That would mean at x equals 12, and the base is moving at a rate of 5 feet per second, and that's away from the house. So we know dx dt is 5. So if I plug that in, I have an x value, I have a dx dt. We're looking to find dy dt. And if I'm looking to find dy dt, that means I also need to know this y value here. So I need these values to plug in. Well, at that moment, the shape of my triangle, if I have 12 and 13, I can determine that the height of that side, using my Pythagorean theorem, is 5. So we'll plug those values in. I've got 2, x is 12, dx dt is 5, plus 2, y is 5, dy dt is our unknown, and we're solving when it's equal to 0. So I have 120 plus 10 dy dt equals 0. And I'll subtract my 120, divide by 10, and that gives me my dy dt. So I get a negative 12 equals my dy dt. and it's negative, that implies it's sliding down. So it's sliding down at 12, and our units of measure here are feet per, I go back up and look at my problem, second. So it's sliding down the wall at 12 feet per second at that specific moment. Okay, so let's continue with part B. Part B says, at what rate is the area of the triangle formed by the ladder and the wall and the ground changing? So at that specific moment, when we say then, we're referring to right at the split second when the base is 12 feet from the house, and we know that rate. Okay? So at what rate is the area of the triangle formed by the ladder and the wall changing? So we're looking the rate at which area is changing. An area of a triangle is 1/2 base times height, and my base and height in this case are x and y. So I have 1/2 xy. So that's my area equation. And in order to find a rate, we're going to differentiate with respect to time. So the derivative of area with respect to time is going to be dA dt equals 1/2. And then in order for us to find the derivative of xy, that's x times y. So we're going to need to use the product rule. So my product rule for the derivative of xy, I've got x times the derivative of y is dy dt plus y times the derivative of x, dx dt. So dA dt equals 1/2 x dy dt plus 1/2 y dy dt, because we distribute. And this problem, or this part of the problem, asked us to find the rate at which area is changing. So that means I need to know what values to plug in for these other 4 variables. And so we have all of those values, and we're talking about those values at the moment when we are 12 feet, the base is 12 feet from the house. So I know what x and y are. My x and y, because we go back to our triangle, my x and y are 12 and 5. And I know my rates, one was given and one we just found in part A. So x is 12, dy dt is negative 12, plus 1/2. My y value is 5. And I'm realizing I wrote dy dt, even though I'm pretty sure I said dx dt. So I'm just going to fix that right there. Dx dt, because that was the derivative of x with respect to time, and dx dt is 5. So I have negative 144 over 2 plus 25 over 2 equals negative 59.5. So the area is shrinking because it's negative at 59.5 feet squared, because that's my unit on area, per second. So we're continuing this problem and talking about part C now, but I went ahead and transferred it over to a new page. And I wrote our equations that are going to always be consistent. Like when we're dealing with the triangle, this ladder is always going to be 13 feet. So we always have x squared plus y squared is 169. The area is always going to be related by 1/2 x times y. And then we have this moment information. We know at 12 feet from the house, the base is moving at a rate of 5 feet per second. So x is 12. Dx dt is 5, and then we found that the rate at which the ladder is sliding down the wall is negative 12, and the rate at which the area is changing. It's shrinking at 59.5 feet squared per second. So part C says, at what rate is the angle changing? So we need to relate the angle to something that we know in this problem. And we want to find the rate at which that angle's changing. And we can set that up because we can say, and we have lots of trig functions, but I'm going to use cosine because we know we're going to be dealing with that 12 value right there. So we can say that cosine of theta is x adjacent over the hypotenuse 13. So I picked to use x, and I don't want to plug my 12 in yet because you know that 12 can change depending on where the ladder is in its sliding process. But I picked cosine because I knew I had that information. I could have also used sine and said opposite over hypotenuse, y over 13. I just went with x because we were given x in the original part of the problem, and x was adjacent to that angle. Okay? So we want to differentiate cosine theta equals x over 13, and we're going to differentiate with respect to time. So d dt of cosine theta equals d dt, and that's the same as writing 1 over 13x. So the derivative of cosine is negative sine, and I have negative sine theta, d theta dt. And the derivative of 1 over 13x is just going to be 1 over 13, and we write dx dt. So considering what we're being asked to find the rate at which the angle between the ladder and the ground is changing. So this angle, and again, we're dealing with that 13 in respect to x. So the angle is changing. The rate at which the angle is changing is this d theta dt. So I need to know what theta is at that moment. And I also need to know what dx dt is at that moment. So I'm going to start rearranging. I've got that d theta dt is negative 1 over 13. I'm dividing by negative sine theta on both sides. Dx dt. And we know that dx dt is 5, right? So we know that value is my 5. But thinking about my problem, we have the triangle with theta, and we've got 12 and 13 and 5. So sine theta is 5 over 13. And that I can plug right in here. So I've got d theta dt is negative 1 over 13, 5 over 13. Dx dt was given as 5. So we end up with d theta dt is negative 1 over 5 times 5, which is negative 1. And that would be radians per second. So it's decreasing at a rate of 1 radian per second at that moment.